Hello, ladies and gentlemen. Today is a very confusing time for me. I thought I had this pinpointed. I was going to talk about Pangaea's north polar orientation, and then my theory was that I'm not quite certain how I got onto it. We'll get off of this crap and look at Google Earth. So here's Google Earth. Don't pay any attention to my yellow line right here yet. Okay, so here's what we're looking at, right? So we look over here, and I had this all figured out. I was like, I've got it. I've got the very beginning story of Earth to get us up to at least the Guacanayabo impactor. And forget it. It didn't happen. I got stumped. I'm like, wait a minute. What's this guy? All right, so let me orient north back up here. Okay, so right here on this little cape, as you might call it, boop, right there, where my hand is on my cursor. All right, that is approximately Earth's, what I perceive to be Earth's original North Pole at the time when Pangaea would have mostly been coagulated at the top of the planet, as the North Pole would have been flying on its galactic flight posture through the galaxy, and then of course the Antarctic would have been exactly the opposite of this coordinate at that time, being the heavier materials similar to hot chocolate and sugar sinking to the bottom of your mug, while the marshmallows stay at the top, but the coffee stays in the middle. You see how that works? So that was my theory, and then I was like, I still couldn't figure out. I know that when we think about the Earth as being entirely molten, the South Pole being colder indicates that, theoretically, the South Pole should solidify at a faster rate than the North Pole, which would place the solidification process coming together and meeting at the center slightly above the equator, because the South Pole would be drying up faster than the North Pole. So it's going to pass the equator before the North Pole reaches the equator, because it's not a equal temperature variant, correct? So we're looking, we call this the planetary suture. Planets are going to have a suture. If you have liquid solidifying at two separate rates, or any rate equal or otherwise, they're going to meet somewhere in the middle before the entire planet has basically solidified the entirety of its shell. So I haven't been able to find what I could actually perceive to be the the planetary suture, at least not in orientation to where the North Pole is today, especially if the North Pole is right here where my little pin is, and bam, right here you have the Svalbard Islands, and they have evidence of 350 million year old tropical forests. So as the theory for those islands goes, they were at the equator at the time that they were flourishing. And here's the thing we might not be considering. Of course, the fossils that we're looking at from those forests, they are not the oldest trees of that forest. Hello, they are the youngest trees of that forest before that forest became subdued by whatever elements caused them to fossilize over the course of millennia. So that means that the youngest trees of said forest at the time of their flourishing, they could have been flourishing for a very long time before that forest became fossilized. So, and we're not going to see the youngest trees of that forest. Why? Because they already grew up, passed away, went back to the earth, became the sea, the fertilization for the new forest trees, and so on and so forth. So we really don't have a clue on how long that forest was in existence. But the thing is, if we look at the mid-Atlantic ridge right through here, and we consider Svalbard Islands as having been at the equator, ladies and gentlemen, that's our planetary suture. The problem I'm running into is my planetary suture isn't running around the entire planet in a clean shot. Once it hits down here where Antarctica is, it gets tore to heck up. So unless it actually transferred or traveled through our current South Pole, Arctic, Antarctic land masses, over to here, back to where it would have been somewhere over here before coming over here, then we got some things to consider. And so here's where we look at the fracture as it comes through. Now we've got a visible line. You can take it from right here, follow my fingertips on my cursor, right across, right through Chukotka, right straight down here to where Japan is. And then of course you have this asthenospheric tsunami down here, which pretty much destroys any evidence of any kind of connection there, right? However, if this is mind you, Mount Fuji is like right up in here somewhere. You follow this. In fact, it's right up this cut. There's a cut right here. And Mount Fuji's right there. Mount Fuji's right at the edge of what might still be the continuation of Earth's planetary suture. And beforehand, I was following it down through here through, and this is where I gave it the Atlapac fracture theory, right? Well, the Atlapac fracture may be possibly correct to some degree, but it's not the planetary suture. So, or even what I'm thinking it is at all, because basically what I perceive to be the Atlapac fracture, ladies and gentlemen, doesn't even go around a hemisphere. All it does is encompass the Americas, and it's only a very small portion of the whole surface of our planet. But if we consider this coming across, then we could bring it over here. And the problem with this one now is that if we try to keep it the same coming across, and and say for instance we're following this as if it was in fact a straight line equator, because it gets really crazy over here doing the zigzags and stuff with Africa and South America. So we could follow this over this direction here possibly, and then it would be basically cutting right through the middle of Australia. Now Australia, I'm saying Australia and Antarctica are once the same continent. When I traced the continents, I couldn't match, obviously, I couldn't match Australia up with anybody up here. A lot has happened up here since Australia moved to this location, and Australia was in this location already before the South China Sea impactor struck the planet over here in the South China Sea. That's why I named it the South China Sea impactor. And so what we have is the world's planetary suture would have cut right through both Antarctica and Australia somewhere through here before coming out, well, maybe right here. And then the problem I'm running into is this wiggity zigzagged garbage going on right here. It's like, whoa, I mean, what's going on here, yo? So, I mean, now, if you look at any person's skull, I mean, you pull their skin back and you look at their skull, you're going to see that their sutures don't grow together in this perfect line. They're kind of funny looking, like somebody really, like Dr. Frankenstein got a hold of them and sewed their skull together. Well, we may have something similar to that taking place with planetary development in its early stages of solidification at the crustal level, and that might be what's happening here, right? But we have basically a general straight line, and we could say that that straight line comes through here. Now, when I went and did my theoretical equator, I brought it right straight through here, and I made sure it was centered between Africa and South America to try to get an idea of some sort of balanced equatorial direction. But yeah, it got a little confusing. So, but when I'm doing this, I'm like, wow, this is complicated, because Antarctica just really takes a chunk out of the Earth's crustal appearance in its vortical rotation here. But you have to understand that Antarctica's vortical rotation was rapid. You don't get spiral density arms like this from an extraordinarily slow process that takes over trillions of years or whatever the case, right? That's obviously an exaggeration. But if you think about it, this kind of energy has to happen quickly for this sort of formation to develop. This is not something that occurs over millennia, period. So now the thing is, and that's my impression, okay? Now, while I was looking at these guys, I began to look over here, and I've always been a little confused about this guy right here. And ladies and gentlemen, this is a good signature of a vortex. Now, the way I was looking at this, because I was trying to establish some sort of orientation that would support the mid-Atlantic ridge as the equatorial suture of the planet, then, you know, basically validating the Svalbard Islands to that extent, or vice versa, then I was like, well, maybe this might have been some, like, the vortex of the North Pole, or maybe the South Pole. Well, you see, it's not rotating in the correct direction to have been the North Pole. So that led me to come to the conclusion that it could only be either a South Pole vortex, which then blows my whole entire Antarctic-Australia theory out of the water, or it is an equatorial vortex. Now, here's the funny thing. If it is an equatorial vortex, then we have a very important discovery here too, ladies and gentlemen. We have two disagreeing vortices, bam, one right next to the other, and they're both equatorial, if that's the case, right? So we have a swapperoo taking place here. Now there's the theory behind the driving forces of the equatorial rotations lies currently, in my mind, lies on their coordinate location in relation to our current equator. So if they're below the equator, if the vortical core falls below our current equator, that means that its driving force is going to be coming from the South Pole. And the vortical density, the vortical spiral density fractures coming out of the vortex, as you see out of Lake Victoria coming right here, indicate and confirm that relationship with the South Pole. But now we have to figure out the orientation of the equator in relation to what I call the ES vortex. I'm calling it the ES vortex because when I first decided to plot this vortex, I didn't know if it was equatorial or South Pole. Okay, so E for equatorial, S for South Pole. So I'm naming it the ES vortex. Now, not even certain that it's a vortex at all in regard to being a primary vortex, because if it is a primary vortex, ladies and gentlemen, that means it has to have a vortical mate on the exact opposite side of the planet that rotates as you look down on it in the opposite direction. So if this one is rotating, in this case, it's rotating counterclockwise, then the one on the other side of the planet is going to be rotating clockwise in order for that vortical core, as my fingers are rotating forward from me, you might say, okay, rotating away from me if you consider they're going away when they reach the top of their rotation. Okay, so that means they're rotating together. That creates a rod between the two vortices. However, the vortices, in effect, are opposites, reciprocals of each other. Okay, so now we're going back to the Hugagget here. This is either a vortex that flipped, and the plan here is my equatorial orientation in relation to this particular vortical setting would mean that it would have to be closer to the North Pole, so that it is the North Pole that's rotating it rather than the South Pole. However, now we know well, let me go ahead and turn on the view here. So I'm going to turn my grid on. All right, we can see that the Lake Victoria vortex falls beneath the equator currently. This is our most current and recent vortex that falls right in line with our current North Pole orientation. All right. But even in as much as you can see, well, I don't know, because I mean, here you have this top yellow line, which is the one I'm referring to. Now, what I can do, I'll tell you what, we'll go down through here. It's all the way down at the bottom. We're going to go ahead and change the colors of my, we're going to change them to, we're going to change them to red. All right, so I'm going to make it red, only for the purpose of this video. And this other one, and these are the tropics, basically. I like to, whatever, whether or not they really are, they can be associated with the current tropics. I don't know. Don't really care. But I'm calling them the tropics because it gives me an idea. I can't use Google Earth and draw pull out a circumference on a circle all the way to where the equator would be for that particular view. I can only go as far as the view I'm looking at will allow me, which creates kind of a tropical line rather than an equatorial line. So here we go. We got my two red guys there. All right, now we can see a little bit easier the difference between the true Tropic of Cancer and the true Tropic of Capricorn, but how these tropics would have been changed in relation to, let's say, this guy right here, his North Pole orientation up here, just slightly off from what it is. Just like these are slightly off from each other. And what we get is we got to imagine where the middle, where the center between here and here is, right? And then we would have to kind of establish. So what we're going to do, we're going to come up here to my diggity wigget. And I'm going to give, yep, it's already set for line. So I'm going to go ahead and draw a line from about right here to right here. Try to make it parallel with that longitude. Or actually that meridian, as it would be referred to properly. Don't know if it really makes that big of a difference. I gotta stop talking because I can't. This is such a touchy situation here. Bam. Alright, so the distance from the ES, Tropic of Cancer, to the ES, Tropic of Capricorn, is a total of 4 million. 4 million, right? Yep. 4,301,269.59 meters. All right. So it's basically 4.3 million meters. All right. So what's half of 4.3? Half of 4.3. Well, we want to be precise about this. I'm thinking about what I want to do. All right. I didn't open that up. All right, so let me go ahead and print this. I'm thinking this out loud, folks, so bear with me. This is good stuff. I mean, I'm sure that someone out there would probably be more than happy to see what it is I'm discovering, because you're discovering it, all right, at the same time I am. All right, and I'm mapping the ES vortices. That's the one I want. I'm drinking my wife's coffee now. New slide. Bam. Boop. Now I've got that one saved. All right. Saving it again. All right. So now we're going to call that the ES Tropics of, oh well, Tropic of Cancer to Tropic of Capricorn distance. Not even sure if it's gonna give me what I need to know, but I have a, that's why when with Google Earth you have to, you know, press your little print screen button to capture that screen, because when you actually save the different graphics on your Google Earth, sometimes it doesn't save quite the information you want to see, and you can't see it again. So we've got that down. Now we're going to go ahead and do our little calculator thingy here. Bloop, 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 bloop. Boom. And we're going to go 4,301,269.59 divided by 2 equals. All right. Oops, there goes my notes. That becomes divided by 2 equals 2 million. Oops, wrong thing. Not 2 minutes, 2 million. Put the comma in the wrong spot. 150,634.795 meters. All right. Now what we're going to do is go print screen. We're going to save that little squiggity-doo, mathematical diggity-dee. New slide. Boop, boop. Save. All right. Now we're going to go ahead and take a next line, and we're going to put it right next to that, and we're going to call it, you know what? I don't need that one visible. Let me take that one out. Beep. All right, so we're going to go here, and we're going to go back to where we want to have it, about up here. And we're going to draw that line down this way here until we reach 2150. Well, that's pretty close. Well, we're pretty close to 2150 right there. All right. Bear with me, folks. I know this is really boring. I got to get in really close to make it easier to adjust. 2150, 634. Nope, still too far out. 634. 636 is close enough, wouldn't you say? As sensitive as this stuff is, yeah. Alright, now we're going to go ahead and zoom out. Alright, there it is. Sorry I couldn't keep it in a straight line. Alright, now we're going to go ahead and look at equatorial. Whoops, wrong guy. Alright. Well, that puts it smack on the equator. Wow. Okay. I mean, that's my plot. And of course, that plot is as close as I could determine the center of this sphere right here, right? I suppose if I wanted to get really technical, I could actually find out where the center of this sphere is. Somewhat. Which, if that's the case, right here, you see where it's right there. But actually, if I think about it, if I'm looking at this and I go to a center, if I was to go into here and click on a point that I visibly see as the center of this arc, if it were a circle, I would be up around in here somewhere, which in this case, that refinement, as we would call it in the artillery, that refinement actually places my vortical core slightly above that equator. Not much, just slightly, but enough that the North Pole would become the driving force behind this vortices. How do you say that? This vortexes, because it's not one. This vortexes. Did I say it was not one? It's not. No, it's not more than one. No, that's what I said. Okay, this vortex is rotation, right? Because it's actually rotating. In the opposite direction, because if we're standing here and our rope is dragging around us to the right, that means we're rotating to the left. Okay, that's how you have to view it. You have to think about these things as if you were standing on the second story of a building looking down on top of the head of your buddy, and your buddy's holding the rope in his hands, and you know, a fairly long rope. Well, maybe not too long, but he's going to have to really spin around fast, because otherwise it's just going to wrap around his body. So imagine your friend rotating to his left, pivoting as fast as he can, and the rope is going to start wrapping around him to the right. This is how you determine the direction of a vortical rotation in relation to the spiral density fractures that you can observe on the surface of the Earth. And there's only so many of them. Why? Because the Earth has only been in a state of worldwide liquefaction under certain and very few extreme circumstances. So who would have been the cause for this particular vortex becoming active in this location at this orientation? That I haven't figured out yet. Now, I was suggesting that we had 4 world-class impactors based on information that I've mapped in the plast. That's right. So here's the thing. Now I'm changing my mind, because the South China Sea impactor had such a massive, devastating effect on the surface of our planet. I decided to give that one a class one step above the class of world class, because it's like, if the other 3 were world class at 56.6 kilometer diameters, and then the South China Sea at I think it was 14 something kilometer diameter or something to that effect. But yet its magnitude's so much worse and greater. I mean, you talk about deep impact. That was a deep impact there, folks. So the thing is, this one was so much worse than these guys. And these guys, they can't all four, that's 2 fingers, they can't all four be world class. So we're going to up the South China Sea impactor to a classification I'm going to call the galactic class. Yeah, right? And then these guys. But that's not counting this vortex as having been affected by any one of these specific impactors yet. There might be a fifth mystery impactor I have yet to discover. Or not. I'm not really sure. I'm piecing all this together as much as I can. And the funny thing about this particular vortex we're looking at right here is that we're going to go ahead and clear this, or we're going to close that out. So I came to the conclusion that I wanted to here. And believe it or not, a vortical core does not have to be very far from the equator to be driven by either the north or south pole vortices, polar vortices. Okay, so there you go. And now we're going to go ahead and shut this view off here. Okay, now when I put these vortices together, they're vortical. I can't figure this out now. My brain's starting to get fried on this stuff. So here we go. Right, this is my vortical perimeter at 45 degrees from the ES vortical core. And funny, look at how it goes. Now it's going counterclockwise. Okay, look what falls in line with it. Okay, so if this was an equatorial vortex, which it was, then we can see that we have the what would be, believe it or not, now this is totally destroying my previous theory. Oh, monkey, a lot of poop. Monkey butt came in. Okay, come here, monkey butt. Mom got up. This is Mama's dog. This is monkey butt. See, she got a monkey butt. So, we're gonna go. I have. Excuse me for just 1 minute. I have to take Monkey out for her morning wee wee, and Boomer likes to go out and do his business too. So we're gonna go. Be right back. Don't go anywhere. All right, come on, Boons. Alright, so I'm back. I just put them outside in their potty pen for a bit. They're just little dogs. We don't want them going out too far because it's actually on the deck. And the deck is covered. Yeah, they're not the kind of dog that you want the seagulls flying around. As it was, a seagull in the news one day took some lady's chihuahua and flew away and ate it for dinner. Well, it just so happens that Monkey Butt is kind of like, we're thinking she's kind of like a Pomeranian or a Pomchi, because she has her nose is too long. It looks kind of like a Chihuahua with uber long hair. Okay, so anyway, back to this, right? I think what I was talking about is, so as I've explained before, when you have the coefficient of solar wind pressure drag, where it causes the continental migration to spiral down in a westward spiral all the way down to the South Pole. And it ends in the process of doing that, it creates continental virga in just the same way that our clouds create their virga on a rainy day. So this is what we're looking at here. And now it creates a very visual effect of why Africa, at the Horn of Africa, is shaped in the way that it is. And this orientation is what would have given Africa its It's teardrop shape, if you want to call it that, right? And coming down like Virgo, which is beginning to make me wonder about my theory of South America and Africa pivoting away from each other toward the South Pole. So now I'm going to come back over this way, and now we come down here. So here we have the South Pole. Now, as you can see right here in Antarctica, very interesting stuff. Right here we have the South Pole orientation as it would have been at the time of the ES vortex activity. And right off of that, you have two of Antarctica's most prominent spiral density arms. And it's like, wow, right there in the middle. And then you come over here to this center, and then you have this one that comes through that core about right through here possibly, and then comes out like something like this, and then comes over here and does this business here. So this is like the current South Pole, of course, where you see it coming together. That's probably just a photographic thing that does that. Not necessarily that you would go down to the South Pole and see this spiraling snow look. Okay, you won't notice that. That's just a picture thingy. So anyway, you have two separate. So that explains why Antarctica has 4 spiral density arms. Now here's what else I began to think about this. I was saying that the north and south polar vortices are anticyclonic because they're spewing material out. I'm beginning to believe that when we have spiral density arms form on the surface of the planet, that means we have material leaving the center of the planet and coming out, and that's when we get anticyclonic behavior. But what I'm not seeing is anticyclonic behavior in the North Pole, because as we see up here, that little pin right there being our current North Pole, there is absolutely no evidence of any spiral density arms of any sort or any kind at all. So if I go to the theory that spiral density arms are the evidence of anti-vortices, then the absence of spiral density arms and, say for instance, more like spiral density fractures become the opposite. They become the indicators of cyclonic vortices. So we might actually be looking at all 4 of the primary equatorial vortices are cyclonic, and the north polar vortex is cyclonic, but only the south pole vortex is anticyclonic. And that might just be because of the force coming through the Earth and the galactic influence with the galactic gravity striking the base of the planet, being the South Pole, and forcing that material out through the back. Basically, it's kind of like the poop, planetary poop right there, and it's heavier. I'm sure they'd appreciate being called poop. But anyway, that's kind of what we're looking at right now, and I'm working on this. I will come back. I know I'm spinning the planet around. I'm looking at it as I spin it around. Hopefully you are too, and I'm not making you dizzy when I do it. So now we have this vortex that falls in line with this spiral density arm of Antarctica, and you're like, wow, right? And, well, who let you in, monkey butt? All right. So then you have the North Pole orientation up here, and you'll notice that this little red dot here is not that far from our current little yellow dot right there. So this was a very recent event. And so that means that if that little cape right there on the Caspian Sea was in fact at some point in time the North Pole orientation, placing this, placing the mid-Atlantic ridge fracture even closer toward a equatorial location, then we really didn't have much migration between these 2 points. That means that this was a very recent effect. A very recent effect, in fact. No, I was going to say it might be related to the North Pacific Oceanic Impactor. But the North Pacific Oceanic Impactor is over here, and the lithospheric stripes, or the Jupiterian stripes that this guy created, puts the North Pole only just a little bit off from this North Pole. So it probably was not the impactor that would have, say for instance, activated this equatorial vortex. So that means this equatorial vortex was activated by something else, either another impactor of similar size, or something else entirely that I haven't been able to put my finger on. And if that's the case, then somewhere in relative to this area here, we would basically see the primary equatorial lithostream traveling as I'm placing my cursor to the left of the screen and following to the right. That's the direction it would be going in, the same direction that the planet would be rotating in. And then that means that we would have basically some evidence, some evidence of lithostream scores, almost as which might be this one right here. You see this score right there, and then we have a score right there. One of these might be the Milan strike that I was trying to map at one point. Now, if that's the case, the only difference here is these scores are just slightly off from this arrangement of the tropics, but not by much. I'm not really sure that and the scores might actually be more accurate in helping to determine the orientation. But if the score is going up here, it may have a different impact here. So let's say we're going to go ahead and take a line, and we're going to figure something out here. So I'm going to put this line right here, and I'm going to go this way, and go like that. Uh-oh, Booms is being bad. There it goes, just like that. Something like that. And then you have... Not quite. It's going up. It's curving up for some reason, when it's actually not. It shouldn't. It should be going down this way if you follow it right. Okay, well, there it is. So I'm going to go ahead and stop this video now, because I don't know what else to do at this point other than basically establish that we definitely have something active going on right here. And I haven't really looked at the perimeter of this to see if it has any kind of indication that it was before or after any certain event. And I don't really have that kind of indication here. However, I mean, you can see how this vortex would have been rotating in this direction here, which is clockwise, and how it seems to be running right along the line. Now, this is the best you're going to get when you come to a tangent in Google Earth. But it's running right along the line. Hey, it's kind of funny how that seems to be running right along that line. Like, there you have your lava flow coming out of these guys. The only thing is, this occurred at a time so much later, I think. Right. That's the algorithm making stuff disappear, I think, anyway. But it might have something to do with that, right? Okay, I'm going to go ahead and stop it where I am here, and so stay with me. If you're interested in learning more about the Earth, we want to do some more planetary forensics. I might not be absolutely correct on everything that I theorize, and I might sound like I'm saying it's fact, but really I'm very willing to change my theories if I find or someone else presents evidence to me that seems to be strong enough to suggest the possibility that what they're telling me could have happened. Then I will change my mind. Just like as an example, we'll come back here. So I was talking about the twin calderas of Yellowstone, and a friend of mine was talking about what he had felt was the case. He doesn't think that they were twin volcanoes, but that one volcano, at some point in time, the volcano had moved from the east point here, where my cursor is, to here, where it is today. And his description of that was quite plausible in what I was believing, because if you put the current vortices together, they come at a tangent in here, down in here and stuff, and you've got the Pacific vortex going up through San Francisco, coming down a San Andreas Fault, to give you an idea, and then the other one's going back, the Sapaliwini is going over here like this. And if you consider the direction of the Nunavut asthenospheric tsunamis as they came down this way right here and flowed down into here, creating these what might have been two volcanoes, but this volcano orientation down here, just in the same way that the Taklamakan supermassive volcano was created, you have this supervolcano created. And over the course of time, the energy, or the flow and the reservoir for that volcano has moved from the east to the west, and it would have done so because of the direction of the vortical rotations affecting it. And then that was plausible. So I could go with, they weren't two simultaneous volcanoes, but one, and one is older than the other. The one over here with the dried out looking, no longer green lava flows versus the possibly the more current lava flow coming out of here. But well, if you think about it, this one looks like it would have affected this whole area, and this one actually looks like it would have been possibly even more recent, because it appears to be primarily well, with the exception of that little gig right there and that gig right there, it looks like this one had something to do with coming over that end, or I don't know, or maybe they take turns. Bam, made this one, bam, made that one, and then this one later was bam, and just went trickle, 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 trickle. Who knows, right? Things that make you go, kind of hard to tell who happened first. Okay, well, anyway, that's what we're looking at. And you see how this has this kind of like ring coming around down. It's sort of like the Appalachians over here, where they have that little ring coming down. This is right on the outer edge of the Sapaliwini vortexes over here, actually. So this one here might have been partly a similar issue, where you have that drainage taking place. Either tsunami, asthenospheric tsunami, or some other reason behind its drainage moving southward. Some kind of liquefied activity. All right, now I'm going to go ahead and stop. There we go. It's probably like 4 hours long or some crazy stuff. So try to remember to click like and subscribe if you like to listen to boring people think about the planet. All right, bye.